All right, so now we're going to talk about limiting reactant problems. This is going to be the same thing that we did in the last lecture, but twice, basically. So what do I mean by that? So this is a type of problem where, let's say that we had a reaction given below. So hydrogen combines with oxygen to make water. Hydrogen gas combines with oxygen gas to make water. And it happens in this ratio where 2 moles of hydrogen are consumed per mole of water, and that generates 2 moles of, 2 moles of hydrogen are consumed along with 1 mole of oxygen, and that produces 2 moles of water. Okay. So if we were trying to calculate how much water was formed, we would start off with how much of the reactants that we have, right? But the chance that I have exactly the correct amount of hydrogen and oxygen so that they react together and that there's absolutely nothing left over is not very likely, right? And so what these problems are all about is figuring out what your limiting reactant is. And that's the reactant that's going to be used up first in the reaction, right? I mean, unless I have the exact same amount or the exact correct amount of hydrogen and oxygen that I mix together, likely there's going to be something left over. There's going to be some hydrogen that's left over or some oxygen that's left over. Something, you know, the likelihood that you get them in the exact balance is not very likely at all. So in these calculations, what you're going to do is 2 stoichiometry calculations to figure out which one of your reactants is the limiting reactant, which one gets used up first, okay? That's going to be our goal. Again, if it gets used up first, it's called the limiting reactant. If it's the one where there's some left over, it's called the excess reactant. And so in addition to figuring out which one is the limiting reactant and figuring out which one is the excess reactant, we can then also ask ourselves how much of the excess reactant is left over. Okay, so these are particularly long problems because you got to do a few calculations for the one type of problem. But let's get into it. It's not too bad. Okay. The idea is this. This is my balanced chemical equation where I have carbon monoxide coming together with hydrogen in order to make what's methanol is the name of this product. So the first calculation that we're going to do is starting with the amount of carbon monoxide I had. So in this problem, it would say something like you start out with 20 grams of carbon monoxide and 10 grams of hydrogen gas. How much product is actually produced? So you got to do 2 different calculations in parallel. One is starting out with the amount of carbon monoxide you have. And then you'll do exactly what we just did in the last chapter, or in the last lecture rather. You'll convert from mass of reactant to moles of reactant using the molar mass. Then you'll jump from moles reactant to moles product using that mole ratio, or again, what the book calls a stoichiometric conversion factor. And then finally, you can get to mass product by using the molar mass of the product, right? So again, going from moles to grams using the molar mass. So you do this one calculation. This is calculation 1. Now you're going to do the exact same thing, but starting out with the amount of hydrogen. So now I start out with my 10 grams of hydrogen gas. That's the moles of reactant 2. I convert to moles of reactant, the mass of reactant 2. I convert to moles of reactant 2 using the molar mass of that reactant. And then I get from moles reactant to moles product using the stoichiometric ratio I get from my balanced chemical equation. And then lastly, to the mass of product that I get using, again, the molar mass. Okay. And so at the end, I have 2 different calculations, 2 parallel calculations. One starting with reactant 1 and the second one starting out with reactant 2. And what I'm going to do is I'm going to compare the values that I get at the end. So what this is saying, what this 22.9 grams is saying, is that if all of my carbon monoxide was consumed, all 20 grams of that carbon monoxide, I would get 22.9 grams of methanol. Okay. Likewise, What the second calculation is telling me is if all 10 grams of my hydrogen gas was consumed, I would end up with 79.5 grams of methanol. Okay, so I'm going to compare these two numbers. And whichever one is smaller, whichever quantity is less, that's how much product is actually going to be produced. Okay, so in this particular instance, it would be, it's not going to be the 79.5. I'm actually going to produce 22.9 grams of methanol. If I mix 20 grams of carbon monoxide and 10 grams of hydrogen gas, I will get 22.9 grams of methanol. I have enough hydrogen to make more than that, right? I have enough hydrogen to make 79 grams, but I don't have enough carbon monoxide. So my carbon monoxide is limiting and my hydrogen gas is excess. Okay, so that's how you do your limiting reactant calculations. It's actually two calculations that you have to do that are in parallel. Figure out how much product would be consumed or how much product would be produced if reactant 1 is consumed. Figure out how much product would be produced if reactant 2 is consumed, and compare those values. Whichever one is fewer, that's how much is actually going to be made. Okay, so let's do an example here. Ammonia is produced by the reaction of nitrogen and hydrogen according to the equation shown below. Determine the limiting reactant and calculate the mass of ammonium produced if 35 grams of nitrogen, so that's this one, is reacted with 12.5 grams of hydrogen. I want to figure out which one's limiting and which one is excess. How much of this ammonia, how much of my product is actually going to be produced if I mix 35 grams of nitrogen gas and 12.5 grams of hydrogen gas? So again, I got two calculations to do in parallel. One starting out with 35.0 grams of nitrogen gas. I'm going to have to convert in order to use my balanced chemical equation, I'm going to have to convert to moles. And so I'm going to have to use the molar mass for nitrogen. Again, I'll give it to you, but make sure you understand how to calculate this. 28.01348 grams per mole. So since I'm trying to go from grams to mole, I'm going to divide by my molar mass, 0.348 grams of nitrogen gas would give me 1 mole of nitrogen gas. And then I'm going to use the mole ratio I get from my balanced chemical equation to jump from moles of nitrogen to moles of ammonia. My balanced chemical equation is telling me that 1 mole of nitrogen gives me 2 moles of ammonia. And then I need to figure out how much, it asks for the mass of ammonia produced. Mass of the ammonia produced. So I need to go from moles of ammonia to grams of ammonia. So again, I'm going to need the molar mass of this equals 17. Okay, so 1 mole of ammonia has a mass of 17.03056 grams ammonia. So I punch that into my calculator. I'm gonna, again, get in the habit, practice now, get in the habit of punching it all into your calculator, all in one line. 35.0 divided by 28.01348 times 2 times 17.03056. And what I get at the end would be 42.5. Going back, paying attention to units, this is how I tell if I've set it up correctly. grams of nitrogen gas cancel, moles of nitrogen gas cancel, then moles of ammonia cancel. I'm left with grams of ammonia. Worrying about sig figs, my starting quantity had 3. My molar masses, because I took all those digits, they're not going to limit me. My mole ratio is exact. So I'm going to mark here. I'm actually not going to round off just yet because I'm going to do my other calculation first before I conclude which one's correct, which one's the actual amount of ammonia that's produced. So now I got to do my second calculation in parallel, but this time I'm going to start out with the grams of hydrogen gas. I need to convert from grams to moles because I'm trying to use my balanced chemical equation. So in order to do that, I need a molar mass. This will allow me to convert from grams of hydrogen gas to moles of hydrogen gas. Now I can use my balanced chemical equation, which tells me that if 3 moles of hydrogen gas are consumed, 2 moles of ammonia are produced. So moles H2, 2 moles ammonia. And then again, it asks for the mass of ammonia. So I'm going to have to use that same molar mass of ammonia, NH3. All right, so I'm going to punch that into my calculator and I'm going to get 70.4016. I'm going to go back and pay attention to units. Grams of hydrogen cancel, moles of hydrogen cancel, moles of ammonia cancel, and I'm left with grams ammonia, which is what I want. All right, you can convince yourself that this also will have 3 sig figs. Okay, and so now what I'm going to do is figure out which one of these is my limiting reactant and which one is in excess. Again, I'm going to do that by comparing the amount of ammonia that would be produced. If all 35 grams of the nitrogen gas were consumed, I'd get 42.6 grams of ammonia. And if all of that hydrogen was consumed, I'd get 70.4 grams of ammonia. So I have enough hydrogen to make 70 grams of ammonia, but I don't have enough ammonia. I don't have enough nitrogen. So the nitrogen is my limiting reactant, and the hydrogen is my excess reactant. Okay, so in terms of answering the first question, which is how much ammonia will actually be produced, that's going to be determined by my limiting reactant. And so I'm going to actually produce 42.6 grams of ammonia. That's my final answer for how much of this will be produced. I have enough enough hydrogen gas to make more. I don't have enough nitrogen gas. Okay, so that answers the first question, which is what's the mass of ammonia produced? The next question is which is the excess reactant? Okay, check, we got that. How much of it will be left over when the reaction is complete? Okay, so if I start out with 12.5 grams of hydrogen, how much is going to be left when it's over? All right, so for this, we need to figure out how much of that hydrogen is actually consumed. Okay, and in order to do that, we're going to again start with our limiting reactant. The limiting reactant is the one that's going to tell, that's going to dictate how much product is produced and also how much reactant is used. We know all of our limiting reactant is used because it's limiting. So there's going to be 0 grams of nitrogen gas left over. But how many grams of hydrogen gas is going to be left over? I know not all 12.5 is going to be consumed. So that's what we're going to calculate. Okay. So again, I'm going to have to make room for myself. You can always rewind if you want to see these calculations worked out, but I got a limited amount of space. So I'm going to have to sort of start over here. I will keep my excess and limiting reactant labels because that's what I'm going to need. So I want to figure out how much hydrogen is actually consumed. Well, I know all 35.0 grams of the nitrogen are consumed. So I can figure out if 35 grams of nitrogen is consumed, how much hydrogen is consumed along with those 35 grams. So I'm going to start this off the same way, converting from grams to moles, grams N2 to moles N2. And now, instead of jumping from nitrogen to ammonia, jumping from reactants to products, now I'm just going to stay on this same side of my equation, but nonetheless, I can do this using my mole ratio, because I know that if 1 mole of nitrogen is consumed, then 3 moles of hydrogen are going to be consumed as well. And then I have to use my molar mass. That tells me that 1 mole of H2 is has a mass of 1.588 grams of H2. Right? So if I punch this into my calculator, I get 7.5559. Okay. Paying attention to units, grams of nitrogen cancel out, moles of nitrogen cancel out, moles of hydrogen cancel out, and I'm left with grams H2. Paying attention to sig figs, I start out with 3 sig figs. Whoops. My molar mass isn't going to limit me. Mole ratios are exact, so that's not going to limit me. And so what I'm left with is 3 sig figs in my final answer. So what this is saying is if 35 grams of nitrogen is consumed, then 7.56 grams of hydrogen is also going to be consumed, right? Based on the mole ratio. And since nitrogen's my limiting reactant, I know all of that's going to be consumed. And so that means with those 35 grams of nitrogen, I'll have this many grams of hydrogen consumed. So now I want to know if I started out, I start with 12.5 grams of H2, and I use 7.559. Remember, we're not going to round until the very, very end. Grams of hydrogen. How much is actually left over? I'm going to have to do a subtraction problem. Because this is a subtraction problem, remember what we do for sig figs for multiplication and division compared to addition and subtraction. Multiplication and division is the easy one. Then you just count the number of sig figs. For addition and subtraction, you have to line it up, and whichever sig fig falls furthest to the left, that's the place that our final sig fig should be. So in this case, I punch it into my calculator and I get 4.944044, something like that. Okay, but I'm going to round that to 4.9 grams of H2 remain. Okay, so remember those sig fig rules for addition and subtraction are different than multiplication and division. So this is what remains. So these limiting reactant problems, there's 2 sort of steps that you would have to do. First is figure out what the limiting reactant is, right? That'll allow you to figure out how much product is actually made. Another thing that I could ask is how much of that excess reactant remains. For that, you got to start out, you got to do a third calculation where you start out with your limiting reactant, figure out how much of the excess reactant is actually consumed, and subtract that from the amount that you started with, right? So I subtracted the amount that was consumed, this 7.5559, from the amount that I started with, which was the 12.5 grams. That gave me how much I actually had remaining at the end.